Okay, good morning. All right, I'll take that. That's good enough. Okay, so we're going to look at a new chapter today, 16.1, chapter 16, section 1. We're done with triple integral for a little while. We're going to switch the gear and look at a couple different things, but pretty soon we're going to come back to all that triple integration. And today is a relatively light day, and that's a nice change. In 16.1, we'll be looking at these things called vector fields. First of all, what a vector field is. A vector field is a function that assigns a vector to each point in space. A scalar field is a function that assigns a scalar to each point in space. And we've looked at scalar fields before, and we're familiar with that scalar field. So for example, a scalar field could be, say, the temperature in this room. Okay, if you have an instrument that you could measure the temperature, you go to each location in this room and you measure the temperature. You're going to get a temperature reading, and that temperature, of course, is a scalar number. It has no direction, just a magnitude. A vector field is just like that. If you have a vector field could be, well, you'll see a lot of examples later, but instead of a scalar, you get a vector, something that has a direction and a magnitude. So let me give you a simple example of a vector field. It has to be a vector function. So a vector function, capital F of xy, and let's just make it very simple. Let's make it xi plus yj. So very clearly you can see that if you tell me what x and y are, so this could be the entire floor of this room, for example. If you give me a point x and y that corresponds to a point on this floor, I can tell you what that vector looks like, which way it points, how long it is, and so on. So let's take a look at what this vector field might look like. At the point 0, 0, this vector is 0i plus 0j, right? So at 0, 0, which is right here, the vector has no magnitude, no direction, just what has a 0 direction, right? No magnitude, so it's a dot. That's the vector we got here at 0, 0. Now let's pick a few more points to kind of see what's going on. At the point 1, 0, for example, the vector is 1i plus 0j. All right, so the point 1, 0 might be over here. And at this point, the vector associated with that point goes one direction to the right and no magnitudes up or down. So it might look something like this. Right, make sense? Let's just pick a few more. At 0, 1, the vector looks like j, right? So at 0, 1, it's going to go like that. At minus 1, 0, it will go this way. At 0, minus 1, it goes down this way. Okay, you get the idea? Pick a point, find a vector. And let's just put a few more down so we get a better picture. At 1, 1, we're going to go 1 unit to the right and 1 unit up. So at 1, 1, the vector will look something like that, right? 1 unit to the right, 1 unit up. At 1 minus 1, it's 1 unit right, 1 unit down. That way. And you kind of get the idea. You can see what's going to happen here. At minus 1, 1, negative 1i, so 1 left, positive 1j, 1 up. Something like that. And also notice the farther you get away, the longer these vectors are. If you go to 2, 2, for example, 2i plus 2j, that's going to make this vector right here much longer than that one. 2i, so 2 units right, 2 units up. So it might look something like that. And this guy, of course, similarly will look something like that. So these guys get longer as they move away from the origin. And we can fill in a pretty complete picture now. Something like this. This is the kind of thing we're dealing with. Okay, let's stop. We can add as many as you want, but we get the picture here. All right, does that make sense? Each point, there's a vector, one and only one vector with a magnitude and with a direction. So this might be something like a light bulb, for example. When you turn it on, light, of course, goes away in all directions from that single point. Make sense? Good. Let's take a look at another example, this time in 3 dimensions, 3-dimensional space. F of x, y, z is equal to, let's make this negative k. We'll make it very simple. All right, negative k is negative 1 in the z direction, so down. And notice that this is a constant vector. At every single point, we're going to get the same vector, negative k. That means whichever point I move to, I'm going to see exactly the same kind of vector going down, like that. They should be connected. And they should be all equal length. All right, you get the idea. Okay, this might represent maybe things like gravity, for example. Suppose that we're looking at the gravitational force in this room. Everywhere we go, we know what gravity is going to do. It really doesn't matter whether I'm here or upstairs in the balcony. Gravity is going to pull me down, straight down, with about the same magnitude in every point in this room. So this could be, for example, gravity on Earth. Okay? Now let me show you a few more examples of vector fields that are used in a lot of applications. So here's an example that shows the water current on Earth. So you see the red ones are the warm currents, the blue ones are the cool currents, and you pick a point on the ocean, let's say right off the east coast, and you see in this area we expect warm current to be going kind of north, and then it's going to follow the coast, go to Europe, and then gets cooler, comes back, and all these things, different kind of things happen. And people track the motion of warm and cool currents because it affects our climate, right? You hear about El Nino and La Nina, that kind of thing. That's going to give you either a warmer winter or a colder winter, etc., etc. So that's a very, very commonly used application where vector fields come into play. I'll just show you a few more examples here. So here, this is showing the flow of water or air, it doesn't matter, around the cylinder. So let's say water is coming this way. Imagine this is the support of a bridge. You have a bridge up here, and then you have this cylindrical support supporting the bridge over a river, and the river is flowing this way. And we're looking at what water is doing. So you can see any point on that river, you look at it, you're going to see the direction and the speed of the water flowing near the support. Obviously, water can't go through the support, so it's going to have to go around. So you see, if you follow along here, it's going to slow down. It has no choice but to slow down, and gets around the support, comes back, and it continues going. And this is the kind of thing that happens when the flow is steady and not very fast. If the flow is very fast, then the flow field will look very, very different. All right, more examples. So similar thing flowing past an airplane wing, for example. So this is a section of the airplane wing. It's called an airfoil, and air is coming this direction. Now, for the same reason, air can't go through that section of the wing. It's going to have to go around. And on the upper surface, you can see air hits the leading edge here, slows down, and kind of hugs the surface, then going around here. Same thing down here. The bottom edge is a little bit more smooth, so the air doesn't get disturbed very much. But up here, we have this kind of shape. And this is how we get lift from our airplane wings. So if you study things like aerodynamics, for example, you'll see a lot of vector fields. You put different kinds of shapes in a wind tunnel, for example, and then you put smoke in there, and that allows you to kind of see how the flow is going. You want more application examples? Yeah, let's keep going. I got more interesting stuff here. I got a little bit more. Okay, so again, another airplane thing, because that's my background. I did my degree is in aerospace engineering, so I got a lot of airplane stuff where calculus is applied to. Okay, so here's a very interesting phenomenon. We're looking at an airplane head-on. Imagine the airplane flying directly at us. Or maybe not directly at us, but we're seeing it coming towards us. Now, we just saw on the last picture how the airflow passed the wing into the page. Now we're looking at this from the perspective facing the airplane. Now you see the airflow kind of curling around the wing tips. What's going on here is because of lift, you have greater pressure down here under the wing than above the wing. That's lift, right? Greater pressure down than up, so the airplane gets held in air. Now, because of the pressure difference, air is going to try to go from high pressure region to low pressure region, like that. So it wants to curl around the wing tips. And then what happens is that these two vortices here will create a very, very long and sometimes very strong wingtip vortices after the airplane. The bigger the airplane, the bigger and more strong those are. And that's why in commercial airports, they try to space out these airplanes sometimes a couple miles apart, especially if the airplane's like a 747, for example. If a smaller airplane gets caught behind the wake, it can easily send it out of control. So following a big airplane, they will space them out very, very far apart. This also causes a phenomenon called induced drag. Because of this curling around, it actually creates a force pushing the airplane against its motion. And it doesn't just happen to airplanes, it happens to birds. Like now at this time of the year, you see Canada geese and other migratory birds flying around. They often fly in the V formation. Now the reason they fly in the V formation, now this is really interesting. Let's look at this picture here. So you have this bird, and it's causing the same kind of wingtip vortices we saw on an airplane. Now those things will create a drag pushing the bird against its motion. A bird following closely behind the leading bird will have the same kind of wingtip vortices happening, and in this region here, those get canceled out. So what happens is that the leading bird will take the entire blunt of the force from the vortices, but the bird behind it gets part of that canceled out. So every bird behind the leading bird is going to have a little bit easier time flying toward wherever they're going. And what these birds do is that they periodically rotate the leading bird out to the back. So the leading bird they always start with the strongest bird to lead, and he or she gets tired, goes to the back, and someone moves forward, and that continues. So they take turn taking the blunt of the force. Bicyclists like doing, for example, the Tour de France, they do the same thing. They also line up in not complete V, but sometimes just a diagonal line. Again, that's the same reason they take the blunt of the leading cyclist takes the blunt of the force, and everybody behind it takes a slightly less drag from that, and then they rotate and so on. So that's why birds flying in that formation is to make it easier for the entire group to go, and once the leading bird gets tired, they rotate, and that continues. Okay, that ends the, I hope, interesting examples I have. Do you like stuff like that? If you do, I can bring more examples for, if appropriate for the future stuff we look at. Is that good? Okay, I'll keep that in mind. A lot of things that we'll be doing after exam 2 are almost directly applicable to aerodynamics. And so, that happens to be part of my background, and I can show you a lot of interesting examples from aerodynamics that deal with what we're looking at. Okay, now let's get back to the simpler stuff here. Now you remember, if you take the gradient of a scalar function, then you get a vector, right? You get fx of xy I plus fy of xy, the partial derivatives, j. And of course, that's the same thing in the three-dimensional world. So what this means is that every time we take a gradient of something, we are, in essence, creating a vector field. And we call this the vector gradient field. So the gradient of a scalar function creates a vector field. And this is called the gradient vector field. Right, because for each single point in space, I can calculate fx, fy, fz. And I can find out the magnitude, the direction, and all that stuff about every single vector associated with every point in space. The function f of x, y, or f 2 or 3 dimension, doesn't matter, is called a potential function. And the reason is because we derive the gradient vector field from some source, and we call that source the potential function. So if the gradient vector field is a force, for example, gravity, then because f exists, that the potential function exists, the force is said to be conservative. It has nothing to do with the political leaning of that force. It's conservative because energy, in this case, is conserved. Right? In gravity, in our gravity field here, you probably know from physics that the sum of potential and kinetic energy is always a constant, unless some other force is involved. So, for example, right now this pen resting here has a certain potential energy and has no kinetic energy. And the reason why it's not going anywhere is because of the surface of this projector. But if I lift it off the ground and I let it go, then it's going to lose potential energy and gain kinetic energy because it's moving until it hits the floor, and then the situation repeats. But at any point, the sum of those two energies is a constant, unless some other force is involved, like air drag, for example, or other wind, that kind of thing. So any kind of force that's said to be conservative, it will keep something constant, some kind of energy constant. It doesn't always have to be, for gravity, it's the total energy. But for electricity, for example, there's some kind of other force, some kind of energy that is kept constant. Hence the name conservative. And in a conservative force field, the work done by that force on something is independent of path. We'll actually see that in a later section of the course. So let's look at just a two-dimensional function for now. If we set it to a constant, then we're going to get a bunch of level curves out of it. Right? Because we get 1 for each k. The relationship between the vector field and the level field, the level curves, is that in places where the level curves are close together, so that could, for example, if you're describing the height of a mountain, for example, if the level curves are close together, that means the mountain is steep, right? In places where they're close together, the vector are longer. And the reason is because these vectors are gradient vectors. The gradient tells you the direction of maximum change and the maximum directional derivative. So in a place where the mountain is steep, the directional derivative up and down the mountain is going to be larger than when in a place when the mountain is flat, right? And conversely, in places where level curves are farther apart, the gradient vectors are shorter. In the limiting case, consider a flat plane. The gradient is just a constant thing, right? It doesn't change. Well, actually, for a flat plane, the gradient, what is the gradient for just a flat plane? Let's say z is equal to 3. What's the gradient? 0, right? So when it's really flat, there's no gradient. The gradient is a 0 vector. So it's very, very short. It's so short that it doesn't have any magnitude. But if any kind of other kind of shape, you're going to get longer gradient vectors. And if you have a surface that has a bunch of these different shapes involved, the same situation is happening. Flatter regions have shorter gradient vectors. More bumpy regions will have longer gradient vectors. Okay, let's take look at a couple examples of gradient vector fields. So here's a function, square root of x squared plus y squared. What shape is this? This is a standard one that you should know. Did you say something? No? Okay, who knows? What's the shape? Cone. Right. All right, so if you have trouble figuring that out, look at what happens if y is equal to 0, for example. Then z is equal to square root of x squared. We're only concerned with the positive root here, so this implies that z is equal to x. So that means every slice of a y constant, you're going to see a line with different intercepts. Same thing with when x is 0, you get z is equal to y, so you get another bunch of lines with different intercepts. So you end up getting a cone out of that. If y is 0, then we get a line like that. If z is 0, we get a line like that. And we end up getting, and each cross-section you can see is a circle, right? So we get a circular cone that looks like that. Now, for getting a vector field, it's not important whether you know the shape or not. But obviously, for integrating things, you need to know the shape so you can set up your bounds appropriately. Okay, anyway, let's get a vector field out of that. Remember, this is fx comma fy. So we're going to get, let's see, x over radical x squared plus y squared, comma y over radical x squared plus y squared. Okay, so what does this look like? If you ignore the denominator for now, you just get x comma y. And we have seen that shape earlier. Right? Ignoring the denominator for now, x comma y looks like this. Right? Things flowing away from the center. So what is radical x squared plus y squared under the x and y? What is it doing to the vector field, to the vectors? Does it change the direction at all? No. What is it going to change? The magnitude, right. So that's one thing we can do to take advantage of what we already have. It's going to have the same general directions as x comma y. That was our first example. And then these guys are just going to change the magnitudes. So what we can see here is that the farther we move away from the origin, the bigger these things will get downstairs. Right? So the denominator will increase the more we move away. The closer we're to the center, the smaller they are. So that's going to tell us that the magnitude of these vectors is going to slowly decrease as we move away. So let's sketch a few ones we can look at. And they'll get a little bit shorter as we move away. Right? Something like that. Right, so this might be a good representation of the light source, for example. The more you move away, the light gets dimmer and dimmer, dimmer. That kind of thing. Make sense? Let's do one more, and then we'll just finish early today. Now, this one will be much harder to sketch. X times e to the minus x squared minus y squared. And let's check out what the gradient is. First, the I component is the partial derivative with respect to x. Right? So the first one here, we need to use the product rule to do it. First derivative of the second plus the second times derivative of the first. That's a 1. The second part is much easier because then that's a constant, x. Derivative of the exponent with respect to y is negative 2y, so minus 2xy e to the that thing. Simplify a little bit. we get e to the minus x squared minus y squared, 1 minus 2x squared. Second thing, we can't do anything about it. Leave that alone. All right, so obviously this one is much more difficult to visualize. We can still kind of analyze what we're going to see. The e to the minus x squared minus y squared, this thing is always going to be positive. And this will, of course, change with the distance. So these things are not going to affect the direction. They will change the magnitude. And they're always positive. So they don't do much. And therefore, the direction will be affected by the parts not involving the exponential. So this and that. These two parts would affect the direction and some magnitude, of course. But these two won't change much of the general shape of the gradient field. Okay, so this is the kind of thing that you really don't want to sketch by hand. It's not a good use of time. So I used MATLAB to sketch the gradient field here. All right, each circle here is a level curve. Each circle is f of x, y equal to some constant k. And if you change the value of k, then you generate different level curves. And then all of these little arrows that are kind of hard to see because there's so many of them, they're so little. But those are our gradient vectors, right? So, like I said earlier, notice that when the level curves are closer together, the magnitude of each vector will be longer than when they're farther apart. There's going to be a faster change when they're closer together. Imagine this is mountain. I think this is one side is coming out, the other side is going into the page. We have seen this shape before. I think way back then, I remember doing a very similar problem with this kind of shape. So you got a mountain coming out and the hole going into the page. But where they meet, there's a very, very steep slope. Coming up, down, very steep. As you move away, things get flatter. So that's why the level curves are farther apart. And notice that eventually these vectors look like dots. We get to a region so flat, they're not doing anything anymore. But here we get much longer vectors. And in fact, it looks like they're going into they're actually flowing this direction. Yeah, so this makes sense now. This is the mountain. This half of the mountain is coming out of the page, and this is a big hole going into the page. So the direction of travel will be going from here from the left side to the right side. If you're on the face of the mountain, if you're not careful, you're going to fall into that pit, right? So that's why the vectors are going in this direction. Okay, so that's all there is to the vector field lesson. It's like I said, it's a light one, it's a short one, and we need things like that once in a while. So that's it. Have a good weekend. See you Monday.
Thanks.